Hi students, welcome to my lectures on thermodynamics. In today's lecture, we are going to discuss about what is the effect of temperature on enthalpy of reaction. In the previous lectures, we have discussed about how to find out the enthalpy of a reaction through heat of formation data or through heat of combustion data. So, in today's lecture, let us find out that let us presume that we already have this enthalpy of reaction data. Then how this enthalpy of a reaction depends on the temperature. If you increase the temperature, what is going to happen? If you decrease the temperature, how the enthalpy reaction is affected by the temperature. To do that, we have to go through some process, some derivation. Finally, we reach to one conclusion. So let us proceed. Imagine a reaction nu1 into A plus nu2 into B gives rise to nu3 into C plus nu4 into D. Nu1, nu2, nu3, nu4 are the stoichiometry coefficients in a reaction. So it is customary to follow that the stoichiometry coefficients of the product has to be taken as a positive and the stoichiometry coefficients of the reactant should be taken as a negative. For example, the reactant stoichiometric coefficients are nu1 and nu2. These two should be taken as a negative number, and nu3 and nu4, which is the stoichiometric coefficients of the product, which has to be taken as a positive. That means nu3 and nu4, for example, has to be taken as a positive numbers. And to convey the message, see the example. Nitrogen plus 3 times hydrogen gives rise to 2 times ammonia. In this, the stoichiometric coefficients of the nitrogen is -1, the stoichiometric coefficient of the hydrogen is -3, and the stoichiometric coefficient of ammonia, it is 2. This is how we have to follow the notation. Enthalpy of any reaction is enthalpy of the products minus enthalpy of the reactants. And if we do that, the enthalpy of the reaction at any temperature, degree representing standard enthalpy of the reaction, T representing the temperature at which we have to find out the enthalpy of the reaction, which is summation of stoichiometry coefficient multiplied by enthalpy of this constituents. Okay, if you summate all the species present in the reaction multiplied by its own stoichiometry, then you get the enthalpy of a reaction. For example, take a same reaction. We know the stoichiometric coefficients of all the chemical species involved in the reaction, and let us apply the formula. Okay, and if you expand, okay, this is sigma, that means all the constituents. If let us expand the sigma, we have 3 constituents here or chemical species. So the first species is nu N2 into enthalpy of the formation of N2 plus nu H2 into enthalpy of formation of H2 as nu N3 into enthalpy of the formation of ammonia. And we already know what is nu N2 is -1, nu hydrogen is equal to -3, nu ammonia is equal to 2. If you substitute in this reaction, you get 2 times enthalpy of the formation, okay, enthalpy of the formation of ammonia at temperature T minus enthalpy of formation of nitrogen plus 3 times enthalpy of the formation of hydrogen. Now you can see enthalpy of the reaction. I told you nothing but enthalpy of the products minus enthalpy of the reactants. You have got this enthalpy of the product, which is ammonia on this, enthalpy of the reactants, which is nitrogen and hydrogen. So the hydrogen. Okay, let us go to. In the next step, let us find out the difference. As you know, the enthalpy is nothing but Cp dt. Okay, if you remember the previous lectures, any enthalpy can be calculated multiplied by 2 terms. One is Cp, specific heat capacity at the constant pressure, multiplied with temperature change. If we take a differential amount, so it will become d of delta HIT. That means standard enthalpy of component I at temperature T. Okay, this is how we have to read. Okay, remember H is equal to Cp dt. Typically you see this kind of expressions in the books, but always remember H means always delta H. Okay, absolute values of the properties is not of use to us, only the change in property is of use to us. So whenever you see single H or single U and think that it is delta H and delta U, and if you that means you can see differential change in enthalpy is nothing but Cpi, that means specific heat capacity of I into dt. You multiply it by sigma nu I on the both sides, you get sigma nu I into d of delta Hi is equal to sigma Vi into Cpi dt. Take the sigma nu I into the differential, okay, then you get d of sigma nu I into delta Hit is equal to sigma nu I Cpi into dt. As we already know, what is sigma nu I into delta Hi into T? Nothing but the enthalpy of reaction. So once you substitute the enthalpy of the reaction in place of sigma nu I delta H into T, then you and you substitute, you similarly sigma V nu I into Cpi is nothing but sigma delta Cp degree is nothing but sigma nu I Cpi. So in place of this, substitute this, in place of this, substitute this. Now you get one equation, okay, connecting the delta H and Cpi. Now integrate from T0 to T. From T0 to T, you have to integrate the expression, because our objective is to find out how the enthalpy of the reaction depends on the temperature. Now we are getting here the term. So integral dx is nothing but x. So delta H at temperature T is nothing from integration from T0 to T. Similarly R into, if you remember this earlier expression, simply I have done is multiplied and divided by R on the right hand side. So keep one R outside and take one R inside. So you get R into delta T0 to T del Cp by R into dt. So what happens to this integral? Enthalpy at T minus enthalpy at T0 is equal to R times integral T0 to T del Cp by R dt. Now take this term onto the right hand side. Now you get enthalpy at any temperature is equal to enthalpy at known temperature plus this integration term. Now you got one expression to find out enthalpy of any reaction at any temperature is nothing but enthalpy of reaction at known temperature plus this integration term. Okay, this integral term is known as IDCPH. In the books, like if you refer to the Smith-Warner's books, this integral has a specific name that is given IDCPH. So if you substitute, that is nothing but delta H at any temperature is equal to delta H at known temperature plus R times IDCPH. That means if you know IDCPH and if you know delta H at known temperature, then you can find out the delta H at temperature T. Okay, this is the final expression. That means this is what we are trying to achieve in this today's lecture. So you can able to find out enthalpy of the reaction at any temperature. Okay, equation 4 is generally used to estimate enthalpy of reaction at a temperature T. In other words, how enthalpy of reaction depends on temperature. Third, if we know the enthalpy reaction at temperature T, then we can estimate the enthalpy of the reaction at any temperature using specific heat capacity data of reactants and products. That means in this del Cp, nothing but heat capacity of the products minus heat capacity of the reactants. If you know the heat capacity data of all the chemical species involved in the reaction, then you can able to find out this integral. Once you know the integral, then you can able to find out delta, that means enthalpy of the reaction at any temperature. So let us find out what is this IDCPH, then what is the expression for this. Okay, if you expand the integral, then what expressions you get, let us find out.